Waves refraction, problem number 35. An electromagnetic wave of wavelength 5.89 times 10 to the minus 7 meter traveling through air is incident on an interface with corn oil, which index of refraction is 1.47. Calculate the wavelength of the electromagnetic wave in corn oil. We are going to solve this problem in 3 steps. Before we go through the steps to solve this problem, I just need to clarify a couple things. One is the electromagnetic wave that is this range 5.89 times 10 to the minus 7 meter is one of the light color, because the wavelength of light, the visible light, ranges from 4 times 10 to the minus 7 meter through 7 times 10 to the minus 7 meter. So there are sections of color of light for each wavelength, for each corresponded wavelength. We are not going to go into which color, which monochromatic color is the one that we are going to study here, but that is the range of the wavelength of the visible light. Another thing to consider is that this is a waveform, and the wavelength is the horizontal displacement of this waveform. So, for the purpose of this problem, instead of electromagnetic wave, I'm going to refer as a light wave. So in this step 1, we are going to calculate the velocity of the light wave and the corn oil with an index of refraction n equal to 1.47. So I'm using a index of refraction formula which includes those 3 variables: speed of the wave in the air, which is represented by C, the index of refraction, and the speed of the light in the medium, in this case, the corn oil. So from this formula, I can derive the speed or the velocity of the light in the corn oil, which is this one. So V is equal C over N. V is equal C over N. So V is equal, C is the speed of light in the air, which is slightly the same as the speed of light in the vacuum, which is 3 times 10 to the 8 meters per second, over the index of refraction in the medium that I want to calculate this velocity, which is 1.47. So now I'm going to use my calculator and calculate this result. 3 divided by 1.47 is 2.04 times 10 to the 8 meters per second. So in this step 1, I calculate the speed of this light wave in the corn oil. steps 2 and 3, I'm going to divide into step 2 is whatever is going on in the air, and step 3 is whatever is going on in the oil. This is the wavelength of this light wave in the air that was given the problem. And this diagram illustrates what's going on here. So this is a light wave that is coming from air to oil. Now there is a couple things that is happening here. One is the air, when you compare the density of air with oil, oil is more dense. We have more particles in the oil. So which means that this wave in that shift of median is going to slow down. So the wave is going to slow down. As it's slowing down, it's going to decrease the wavelength. So the wavelength in the air is this long. In the oil, we are going to predict that will be smaller than this because this material is more dense and the wave is going to slow down. Another thing that happened here is the frequency. So the frequency in the air and the frequency in the oil section remains the same, will not change. But the wavelength and the speed is going to change with the change of medium. So the frequency of this light wave in the air and oil is the same, and the speed of this light wave in the air is 3 times 10 to the 8 meters per second, and the speed of this light wave in the oil is 2.04 times 10 to the 8 meters per second, which is less than the speed of this light wave in the air. So let's pause our step 2 and go to step 3, which is the objective of this problem, to calculate the wavelength of this light wave in the oil. We have this formula that is the speed of a wave in terms of the wavelength and the frequency. So we can derive a formula for the wavelength of the oil in terms of the speed of the light in the oil over the frequency of this light in the oil. However, I don't have this information. I do have the speed, but I don't have the frequency. But I have enough information here to calculate the frequency of this light wave in the air, because in the oil is the same and I can't replace here. So the speed of this light in the air is the velocity of this light wave in the air over the wavelength of this light wave in the air. And I have all the information. So the frequency in the air is the velocity, which is 3 times 10 to the 8 meters per second, over the wavelength, which is 5.89 times 10 to the minus 7 meter. So I cancel meter with meter, and I have 1 over second, which is the unit for hertz. So the frequency of the air is, using my calculator, is 3 to the 8 divided by 5.89 to negative 7. So here we have we can round this 5.1 times 10 to 14 hertz. So that is the frequency of the light wave in the air. Great, now you finally can calculate the wavelength of this light wave in the oil. So the wavelength in the oil is the velocity of this wave in the oil over the frequency in the air, which is in the oil, but since both are the same, I'm just gonna go ahead and copy this value right here. 5.1 times 10 to 14 hertz, which is second. So that's why we cancel 1 over second. So we cancel these second units here, because this is 1 over second. We cancel out, and the answer should be in meter. So we are gonna use my calculator, and I already have that information, but I'm gonna do slower. 2.04 EE to the 8 divided by 5.1 EE to 14. So to write in scientific notation is 4 times 10, 1, 2, 3, 4, 5, 6, 7, minus 7 meter. So that's the final answer. And our result makes sense because the wavelength in the oil is less than the wavelength in the air.